In statistics, missing data, or missing values, occur when no data value is stored for the variable and in observation. Missing data are a common occurrence and can have a significant effect on the conclusions that can be drawn from the data. Missing data can occur because of non-response, no information is provided for several items or no information is provided for a whole unit. Some items are more sensitive for non-response than others, for example items about private subjects such as income. Dropout is a type of missingness that occurs mostly when studying development over time. In this type of study the measurement is repeated after a certain period of time. Missingness occurs when participants drop out before the test ends and one or more measurements are missing. Sometimes missing values are caused by the research error, for example, when data collection is done improperly or mistakes are made in data entry. Data often are missing in research in economics, sociology, and political science because governments choose not to, or fail to, report critical statistics. Types of missing data. Understanding the reasons why data are missing can help with analyzing the remaining data. If values are missing at random, the data sample may still be representative of the population. But if the values are missing systematically, analysis may be harder. For example, in a study of the relation between IQ and income, participants with an above-average IQ might tend to skip the question "What is your salary?" Unregistered trademark analysis may falsely show no association between IQ and salary, while in fact there may be a relationship. Because of these problems, methodologists routinely advise researchers to design studies to minimize the incidence of missing values. Missing completely at random values in a dataset are missing completely at random if the events that lead to any particular data item being missing are independent both of observable variables and of unobservable parameters of interest, and occur entirely at random. When data are MCAR, the analyses performed on the data are unbiased. However, data are rarely MCAR. Missing at random missing at random occurs when the missingness is not random, but where missingness can be fully accounted for by variables where there is complete information. MAR is an assumption that is impossible to verify statistically, we must rely on its substantive reasonableness. An example is that males are less likely to fill in a depression survey, but this has nothing to do with their level of depression, after accounting for maleness. Missing not at random missing not at random is data that is neither MAR nor MCAR. An example is if men fail to fill in a depression survey because of their level of depression. Graphical models can be used to describe the missing data mechanism in detail. Techniques of dealing with missing data reduce the representativeness of the sample and can therefore distort inferences about the population. If it is possible, try to think about how to prevent data from missingness before the actual data gathering takes place. For example, in computer questionnaires it is often not possible to skip a question. A question has to be answered, otherwise one cannot continue to the next. So missing values due to the participant are eliminated by this type of questionnaire, though this method may not be permitted by an ethics board overseeing the research. And in survey research, it is common to make multiple efforts to contact each individual in the sample, often sending letters to attempt to persuade those who have decided not to participate to change their minds. However, such techniques can either help or hurt in terms of reducing the negative inferential effects of missing data, because the kind of people who are willing to be persuaded to participate after initially refusing or not being home are likely to be significantly different from the kinds of people who will still refuse or remain unreachable after additional effort. In situations where missing data are likely to occur, the researcher is often advised to plan to use methods of data analysis methods that are robust to missingness. An analysis is robust when we are confident that mild to moderate violations of the technique's key assumptions will produce little or no bias, or distortion in the conclusions drawn about the population. Imputation equals. If it is known that the data analysis technique which is to be used isn't content robust, it is good to consider imputing the missing data. This can be done in several ways. Recommended is to use multiple imputations. Rubin argued that even a small number of repeated imputations enormously improves the quality of estimation. For many practical purposes, 2 or 3 imputations capture most of the relative efficiency that could be captured with a larger number of imputations. However, a too small number of imputations can lead to a substantial loss of statistical power, and some scholars now recommend 20 to 100 or more. Any multiply imputed data analysis must be repeated for each of the imputed data sets and, in some cases, the relevant statistics must be combined in a relatively complicated way. Examples of imputations are listed below. Partial imputation equals. The expectation-maximization algorithm is an approach in which values of the statistics which would be computed if a complete dataset were available are estimated, taking into account the pattern of missing data. In this approach, values for individual missing data items are not usually imputed. Partial deletion equals. Methods which involve reducing the data available to a dataset having no missing values include listwise deletion, casewise deletion, pairwise deletion. Full analysis equals. Methods which take full account of all information available, without the distortion resulting from using imputed values as if they were actually observed. The expectation-maximization algorithm, full information maximum likelihood estimation. Interpolation equals. In the mathematical field of numerical analysis, interpolation is a method of constructing new data points within the range of a discrete set of known data points. Model-based techniques, often using graphs, offer additional tools for testing missing data types and for estimating parameters under missing data conditions. For example, a test for refuting MAR-MCAR reads as follows: for any 3 variables x, y, and z where z is fully observed and x and y partially observed, the data should satisfy. In words, the observed portion of x should be independent on the missingness status of y, conditional on every value of z. Failure to satisfy this condition indicates that the problem belongs to the MNAR category. Remark: these tests are necessary for variable-based MAR, which is a slight variation of event-based MAR. When data falls into MNAR category, techniques are available for consistently estimating parameters when certain conditions hold in the model. For example, if y explains the reason for missingness in x and y itself has missing values, the joint probability distribution of x and y can still be estimated if the missingness of y is random. The estimand in this case will be where and denote the observed portions of their respective variables. Different model structures may yield different estimands and different procedures of estimation whenever consistent estimation is possible. The preceding estimand calls for first estimating from complete data and multiplying it by estimated from cases in which y is observed regardless of the status of x. Moreover, in order to obtain a consistent estimate, it is crucial that the first term be as opposed to. In many cases, model-based techniques permit the model structure to undergo refutation tests. Any model which implies the independence between a partially observed variable x and the missingness indicator of another variable y, conditional on, can be submitted to the following refutation test. Finally, the estimands that emerge from these techniques are derived in closed form and do not require iterative procedures such as expectation maximization that are susceptible to local optima. See also, censoring, indicator variable, inverse probability weighting. References: ABCD Adair, H.J., Menberg, G.J. 2008, Messner S.F. Exploring the Consequences of Erratic Data Reporting for Cross-National Research on Homicide. Journal of Quantitative Criminology 8, 155 173 doi, 10.1007/BF01066742. A.B. Pollitt D.F. Beck Court. Nursing Research, Generating and Assessing Evidence for Nursing Practice, 9th ed. Philadelphia, USA, Walters Clough Health, Lippincott Williams and Wilkins. http, missingdata.lshtm.ac.uk/ Index.php option equal com underscore content ampersand view equal article ampersand ID equals 76% 3 a missing dash at dash random dash mar ampersand cated equal 40% 3 a missingness dash mechanisms ampersand item at equal 96, Little, Roderick. Statistical analysis with missing data. Hoboken, New Jersey, Wiley. ISBN 978-0471183860. A. B. Moen, Karthika. Pearl, Judea. Tian, Jin. Advances in Neural Information Processing Systems 26 pages 1277 Euro 1285. Calvane, Juha. Study Design and Causal Models. Scandinavian Journal of Statistics 42, 361 Euro 377 doi, 10.1111/Stros 12110. Graham J. W., Olkowski A. E., Gilreath T. D., How many imputations are really needed? Some practical clarifications of multiple imputation theory. Preventative Science 8, 208 Euro 213 doi, 10.1007 per second 11121-007-0070-9. Moen, Karthika. Pearl, Judea. On the Testability of Models with Missing Data. Proceedings of ASTAT 2014, forthcoming. Darwish, Adnan. Modeling and Reasoning with Bayesian Networks. Cambridge University Press. Pothoff, R.F. Tudor, G.E. Pieper, K.S. Hasselblad, V. Can one assess whether missing data are missing at random in medical studies? Statistical Methods in Medical Research 15, 213 Euro 234. A. B. Pearl, Judea. Moen, Karthika. Available at http ftpcsuclaedu.backslash/serif417 PDF Recoverability and Testability of Missing Data, Introduction and Summary of Results. UCLA Computer Science Department, R417. Moen, K. Van den Broek, G. Choi, A. Pearl, J. An Efficient Method for Bayesian Network Parameter Learning from Incomplete Data. Presented at Causal Modeling and Machine Learning Workshop, ICML 2014. ADR, H.J. Chapter 13, Missing Data. In ADR, H.J., and Melnberg, G.J., Advising on Research Methods, A Consultant's Companion. Huizen, the Netherlands, Johannes van Kessel Publishing. ISBN 90-79418-01-3, Stoop, I. Billiot, J., Koch, A., and Fitzgerald, are Improving Survey Response, Lessons Learned from the European Social Survey. Wiley. ISBN 0-470-51669-0, Zarat L. E., Nogueira B. M., Santos T. R. A., Song M. A. J. Techniques for Missing Value Recovering in Imbalanced Databases, Application in a Marketing Database with Massive Missing Data. IEEE International Conference on Systems, Man and Cybernetics, 2006. SMC 06 pages 2658 Euro 64 doi, 10.1109/ICSMC. 2006.385265. Further reading, Rubin, Donald B. Little, Roderick J. A Statistical Analysis with Missing Data. New York, Wiley. ISBN 0-471-18386-5. Enders, Craig K. Applied Missing Data Analysis. New York, Guilford Press. ISBN 978-1-60623-639-0. Allison, Paul D. Missing Data. Thousand Oaks, Sage Publications, Incorporated. ISBN 978-0-7619-1672-7. Acock A.C. Working with Missing Values. Journal of Marriage and Family 67, 1012 Euro 28 doi, 10.1111 per joule 1741-3737.2005.00191x. Van den Broek J., Cunningham S.A., Eccles R., Herbst K. Data cleaning, detecting, diagnosing, and editing data abnormalities. PLOS Med 2, E267 doi, 10.1371/journal PMED. 002067. PMC 1,198,040. PMID 16,138,788. Schaefer, J.L. Graham, J.W. Missing Data, Our View of the State of the Art. Psychological Methods 7, 147 177 doi, 10.1037/1082-989x7.2.147. PMID 12,090,408. Graham, John W. Missing Data Analysis, Making It Work in the Real World. Annual Review of Psychology 60, 549 doi, 10.1146/AnnuaryPsych. 58.110,405.0855530. Rubin D.B. Inference in Missing Data. Biometrica 63, 581 doi, 10.109,363.3.581. External links. Background Missing Values in Vision, fsitchwiki.com, Missing Values, Identifying Missing Values, and Dealing with Missing Values, missingdata.org, Department of Medical Statistics, London School of Hygiene and Tropical Medicine. Software MPLUS, PROCMI and PROCME Analyze, SAS, SPSS.